Good evening, everyone, and welcome to N Simplex Pachinko. This is Obi-Wan Pez. We are going to be hanging out this evening and doing more math stream. Tonight I was looking at doing some redefinition of some of the trigonometric functions. I worked out with some of my students in class this time. I think it was last week. How to look at the beginning of trigonometry, and rather than thinking about this as always, here's sine, here's cosine, here's tangent, I kind of reformulated it, and I think it worked. Guess we'll see. Find out how their homework is later. And like I said, hey Superbrain, how you doing? Good evening. And let's see. Alright, weird. Okay. So yeah, I'm looking at changing stuff up, seeing how things are going. That's really kind of like it's really kind of one of my only jobs at that college. I mean, it's not like it's redefining trigonometry or anything. It's just a matter of looking at it from a different perspective because, you know, some of the students are not. They've been getting the same old kind of song and dance for a very long time. And I wanted to see if we could change this up a little bit and get them to see things in a slightly different light. So we'll see how it goes. So anyway, ignore me and my collatsing. Alright, so really do I need to do this every time? There's got to be a way to set default. Alright. Numerical simulations, ODEs. Is it a numerical solution? So the one that you actually had to like do out that way, or this is fine. There's only like 2 things that I actually miss about using Zoom at school. One of which is drawing a shape. Symbolically, okay. Yeah, Wolfram tends to just pop up a solution sometimes and be like, here you go. seriously. Like, and this is the worst part, is like, I know what the circle values should be. I know what the unit circle values are. So, like, I should be able to do this with basically zero effort. But, anyway, I digress. Yeah, because that doesn't do anything. Alright. So anyway, if we take this and we say, we're just going to take some random line. It's going out like this. This is going to be our get our standard Cartesian coordinate axes. Right here. We have our theta in standard position, so we're starting from the positive x-axis and then going in the counterclockwise direction. So when we do this, right, we have an intersection point on the circle, which is going to be defined by x comma y. We are going to assume that technically our radius could be anything, but r equals 1 is the most convenient. So we'll stick with that for now. How's the music, by the way? Is it too loud or doing okay? And then when we do this, we now have some ways to define measurements of the circle. Yeah, well, yeah, that's the problem, is that I am peeking myself into the yellow, and it's still not doing it. Aha. How's that? Any better? Okay. Too much or... Okay. So I found the audio setting. Yep, there we go. Okay. So my problem is that, like, for whatever reason, my microphone never actually went up into that range. And so, yeah. No. So, like, I went into the audio settings, the main audio settings, and, like, tweaked everything and put my mic up to maximum. And I went into my IQ, both. So I went into Windows settings. I went into my IQ settings for the headset. I went into the OBS, like, general settings and turned them all up to maximum for the microphone. And that was what I had. I just found, though, the advanced audio properties on the mic aux level popped up with this nice little thing that's like, how do you want to affect your... Yeah, how do you... What setting do you want for all of these things? And currently desktop audio is set for negative 30 decibels. And mic aux was set for 0, so I popped it up to 10. And apparently, that seems like it's good. Well, anyway. At any rate. Okay, so if we set up the unit circle like this, most of the time what we're going to be doing here is saying, well, the traditional approach to this is saying, I want to drop an altitude from this location. It's going to hit onto my positive x-axis, make a right angle, and then from here we want to look at this right triangle here. Yeah, I also don't know if I'm too loud or not, because I can't actually... I can hear myself through the microphone, I can't hear myself through Twitch. Yay. Although I guess I can do this. Yeah, right. Maybe a little bit down. Anyway. But let's turn it down to here and positive 10 in the settings. That's going to be weird. Anyway. So, most of the time we concentrate on this triangle right here and say, okay, this is going to get us the cosine of theta there, sine of theta there, and then r equals 1 along this side. And then we can start working on, getting all the rest of the trig functions. But this semester I was like, this isn't working for me. And it seems to not be working for most of my students. And trying to come up with, sine and cosine and all that good stuff. Trying to define it off of theta just wasn't really making any sense. So I said, okay, let's, instead of doing this, right, the ratio of the opposite side of that angle to the radius of the circle or the hypotenuse of that triangle. Most of them at least have that pretty well stuck in their heads. That particular ratio is going to be the sine function. So sine of theta is equal to, as it turns out here, y over r. So we get this value here, which is our y value. Our r value here is 1 on the unit circle. So the sine of theta is equal to the y value itself. So this is a handy shortcut. And like I said, as always, you can define this specifically as like, this is this particular triangle, and then on the unit circle, this is going to be a similar triangle, just totally similar to that. It's fine. There you go, just nuke it all, start over. Right, so then here we've got whatever radius we want there, r, whatever our y value is here for that particular one. And then here on the inside, we end up with this 1 value. And this is going to be the sine of theta. So here the sine of theta divided by 1, right? Small to hypotenuse. We're going to go y to r, small to hypotenuse. And that gets us a nice unit circle definition that is based off of similar triangles. It also sets the stage for finding all the rest of them. So on the unit circle, the sine of theta is equal to the y value, and otherwise it's just y divided by r. Okay, fair enough, right? Everybody knows that pretty much. Anybody who's taken trig knows that one. All right, then I said, what we're going to do is instead of work on, again, cosine and all the rest of them, now we're going to define the rest of the functions. So, one of them is going to be defined as here, the length of the tangent line that goes from the side of the circle up to where the terminal side of this angle is going to cut through it. So it's going to cut through the terminal side of the angle, will cut through the vertical tangent somewhere. And then here, it's in the positive direction. So this is going to have a positive tangent value. Which means that the tangent of theta, again, here we can do this as, like, we can do this as the similar triangles, the same thing that we did here. I kind of did that backwards, didn't I? Because I said that was going to be... Alright, whatever. We'll make it work. Take that one out. So this is just R. Maybe? I'm playing games that are in a time loop, so I mean, I might as well do my math in a time loop as well. Right, so we want to compare, like, our tangent of theta to y. And then we can compare our fifth steps. No, actually not one. Let's have that be r again. Let's have this be x. Anyway, yeah, so tangent of theta. Oh, that's what the problem is. Yeah, this is r tangent theta. Okay, that was my problem. So how did I get that one? Because I defined it on the basic. Okay. Right, okay. So here we go. So if we do the same thing here, this one is going to be 1, because that is going to be the tangent. It's going to be vertical tangent. It's going to be our y value, our r value, and our x value. There we go. So tangent over y is going to be equal to 1 over x, given that, again, this is going to be the unit circle here, going out to the tangent line. And then here, this is whatever circle we're actually on. Again, without loss of generality, could be larger, could be smaller, doesn't much matter. And this is going to be 1 over x is going to be our two comparative sides. Smaller to larger, smaller to larger. Tangent theta to y is equal to 1 to x. Alright, so then that gets us tangent of theta is equal to y over x. Yeah, last week I was using the new tablet because I had just gotten it, and it's working out very nicely at school. Finally got all the drivers updated because I'm not a sysadmin. And they were so busy it ended up taking them like 3 days. So now I have the same old one that I have always had, but now I'm not carting it back and forth and possibly forgetting it. So that's always a plus for me. I mean, I only forgot it a couple of times, so you know. Yeah. So the new tablet is very nice. I must say it has the the pen is something like 4K resolution. So I mean, you might have even seen it when I was doing the collapse thing just now. Probably not, but you never know. You can even see it right there. We got like the old stuff right here, and this is the new stuff with the new. Um, why didn't that work? Yeah. So like this branch here is all the new stuff with the new tablet, and this is the new stuff that I just did with the old tablet. So you can maybe see a little bit of a difference between them, apart from just being thicker. I think like the higher resolution allows a much cleaner picture. And yeah, you can see like the 3 here is a little wobbly. Part of this 13 and this 3 here. These are all old, and then this is the new resolution. And a little bit here. The 2 and the 6 are very nice. I don't know what happened to the 3 there. Yeah, and I mean this one does too a little bit. So like I can I can vary the size of the line by how much I press. Oops. And I can also break my tool. Uh, it's fine. Somewhat. Let's see. So if I go like this. Yeah. I don't see much of a change just in angle. So at least with the old one. There's a little bit at the beginning here, but I think that's mostly because I had changed pressure more than angle. But like all this is almost the same. So maybe the new one might also have something to do with angle. Yeah, I'll have to check it. So once school gets out in the um, you know 10th to 15th, somewhere in that neighborhood, I'm going to be taking the new one back here and start like maybe cranking out some videos. Maybe. Um, well, I shouldn't say the 15th because then I'm going to be correcting. No, like, okay, so the 10th is the end of classes. So from the 10th to the 15th, I'm going to try and knock out all of my grades so that I only have to correct the finals, and then hopefully I'll be able to get the wrong one. Yeah, well, I mean, I can just switch them, right? So then so I'll have the old one waiting for me at school just in case. And then I can have the new one at home to do awesome videos with. It's fine. Okay. All right, so then my point was here we could do this distance here as what's going to be now, define the going from the origin out to the tangent as the secant. So this is going to be the secant of this circle because it's going to go through the circle twice, right? One on either side of it. And in this particular case, we usually just define that length as the secant function in terms of theta. So rather than saying like, this is going to be the secant line, goes through both of these locations here and here, and then meets up with a vertical tangent on this side in this location. This is on the opposite side of the circle, so it's going to do something different. At any rate. So this is going to end up being, again, Right. So that's going to be our secant of like the unit circle, and then we compare that to, again, the xy values for the unit circle. So here, if our unit circle is, I made that bigger. Sure, why not? So if our particular unit circle has this x, y, and 1 right triangle, then the secant, tangent, and radius triangle is also going to oh man, I am having a day. I did this backwards again anyway, didn't I? So whew. Alright, so the secant goes for secant for the unit circle. We'll go outside, which means that the bottom side is going to be r, is going to be 1. And I don't care about y. But alright, let's back that up then. Alright, so for this, if this is going to be the tangent of theta, this is the secant of theta. Yeah, okay, we're good. This is going to be y, this is going to be x, and this is going to be 1 for the unit circle. I'm not doing the unit circle here. Okay, again, xyr is going to be generic. Okay. And then the secant, tangent, and 1 is going to be for the unit circle specifically. Okay. So let's define the secant by using the unit circle. There we go. And then xyr is going to be any generic circle. So we scale either up or down to get our unit circle secant tangent 1. So then here, the secant can be defined with r, right? So secant of theta over r is going to be hypotenuse over hypotenuse, and then is equal to large horizontal is 1 compared to small horizontal is x. Okay. This took longer for me to do the mental gymnastics in my head than it did anything else. Alright, so then on the unit circle, we had that the sine of theta was just equal to y. The tangent of theta doesn't change at all. It's going to still be y over x. And the secant of theta is going to be 1 over x. Yes. Right, so we don't... did you use the square root of x squared plus y squared or something like that in this place? I mean, it also works, but... So anyway, the sine of theta is going to be equal to just the height of this triangle, so the y value. the secant of theta ends up being 1 over x, which is really weird in terms of like trying to figure out what exactly that's supposed to mean. But there's a number file video that did some cool stuff. Touche. Power series. Yeah, no, that could be okay. That could work. Yep, we're gonna be doing. I'm gonna be doing power series tomorrow with my Calc 2 class. So we did the basic introduction yesterday, and now we're gonna be doing the Taylor series, and then, like I said last time, I want to do pate approximants, and like just give them a little taste. It's not part of our curriculum or anything like that, and I only just found out about them, so just very, very briefly do a little quick thing. E to the I phi. Okay, so there was a number file video that dealt with inverses. And so trying to like draw the inverse length is really weird when you're trying to do stuff like this. So there's like a special tool that I think it was Alex Bellos. No. What's his name? No, I'm not gonna remember. I'll know his name when I see it. Yeah, Simon Pompena. Yeah, it was an old video, like one of their first couple years or so. So Simon had a tool that it's like a compass, but when you stretch it out to do like the radius, it actually makes the third part like go show you what the length of the inverse would be. So like as you move the radius out, the other part comes back in, and as you move the radius in, it starts moving the other piece out. So it creates an inverse, and it was a weird sort of thing. It's like inverse circles or something like that. Epic circles. Yep. So Epic Circles is a good video if you watch that at some point, and he uses that tool. So I found it very interesting. It was, again, strange but cool. All right. So then I also define the tangent here based on what I've talked about this many times on this channel before, but the tangent of theta can be looked at with this y over x, which is the ratio between the two distances. Cool, okay, whatever. But, and then I say, well, remember that you're going through 2 points, x comma y and 0 comma 0. What does this look like? And invariably, I shouldn't say invariably, most of the time students get this, where I'm going with this, because this is y, this is x, and we have a 0, 0 here. So this is like the same thing as going like this and saying y minus 0 over x minus 0. And then somebody will be like, oh, that's slope. So the tangent of theta, the distance between this point here and this point here on a unit circle, can be thought of as the exact same value as the slope of the terminal side of the angle. So as you come up further this way, we end up having longer and longer tangent lines that are going to be the measurements from this intersection point all the way down to 1, 0. So then we see that, again, the distance keeps increasing, and as we get higher and higher angles, the distance keeps increasing until it becomes parallel, right? Then it's infinitely long, and we no longer have a slope of the line. The slope is undefined, and as is the distance along the tangent until it intersects with this particular line. So we can define this by slope, we can define this by the height of that inner triangle, and then we can define this as like the inverse of the horizontal distance. So now we have the three main trig functions. And some of my students were like, no, hang on a second. And I said, no, look at the naming convention, right? This is the sine, the tangent, and the secant. These are not, like, they are unique names. They are by themselves. You can't say that these are named after something else. So these are the three main functions. After a little more protest, yes, of course, they have partners, which we can also label here. That's better. Ish. I mean, sure, you could also say that there's no such thing as division or subtraction. But we've just developed a nice little shortcut of calling it division and subtraction in order to make it a little bit easier to help, other people learn mathematics. And I mean, whether or not you personally find use for any particular trigonometric function, somebody else could be like, well, I found a lot of individual, I found uses for this thing. So, for instance, when you're doing calculus, right, what are the derivatives and integrals of these things? So, like the derivative of the sine function is, we say, this cosine function, so we could field, maybe? I think it's field in English. Addition, subtraction, multiplication, division are all defined and behave as corresponding operations. Yeah. It's been an awfully long time since I've done any abstract algebra. So yeah, anyway, when you're doing calculus, a lot of times it's like, okay, well, if I take the derivative of sine, I'm going to get what we call cosine. But, is it necessary that it is its own function? I mean, it's a nice convention, because I would not like to say that the ddx of sine of x is equal to the sine of pi over 2 minus x. That seems rather inconvenient. I don't know. Right, and then derivative of a tangent is going to get you secant squared. So again, you could, in theory, get away with saying it's just 1 over a cosine squared. But again, why not make it its own thing? And especially if somebody is going to say, like, I need to know what the measurement is here for this particular length. And again, if you find it helpful to measure the length from the origin out to the tangent line, right, then you're going to want to call that by its own function name. And same with the tangent, right? What's the length of the tangent line that is cut by the extended terminal side? So I don't know. I don't necessarily need all of them, but at the same time, it makes a nice convention. All right, so then if we draw a horizontal tangent rather than vertical, mark this point, and now do everything corresponding to this angle rather than this one down here, then we end up with a right triangle here which has by parallel lines with a transversal cut through, this angle theta is going to be up here as well, which on both counts is going to make this angle here the complement of theta. So our pi over 2 minus theta. And then when we draw this part, let's just clean this up a bit. We can draw a right triangle this way instead. Pi over 2 minus theta. Which a lot of times, like, I just label as some other angle, so like alpha. So if we want to do this, then we can say now we want all of the same trigonometric functions, but done on alpha instead of theta. So, right, the sine of alpha, see, tangent of alpha, secant of alpha. Again, here, this can be done as r, this can be our x, this can be our y. So our sine of alpha is going to be x over r. Our tangent of alpha is going to be this length, but then scaled down. So this is our r tangent alpha, or r tangent alpha. This is r secant alpha. So again, if we scale everything down, tangent alpha is going to end up being opposite over adjacent is x over y. And then secant of alpha is going to be 1 over y. R over y, sorry. Hidden in that song? Yeah. So then each of those, we could just rewrite alpha as pi over 2 minus theta, and then get it in terms of theta specifically. So then this was all defined as now, instead of the sine of the complementary angle of theta, this was now the complementary sine of theta, and the complementary tangent of theta, and the complementary secant of theta. So anyway, it makes it, again, a nice little convention to just say, like, oh, well, this comes from all of these. This comes from all of these setups. So the same sorts of things that we had for our other triangle on this side. Sorry, triangle on this side, where we have our vertical tangent. Right, we now have our horizontal tangent, which then defines the complementary angles trig functions. So I liked doing this part for my students this time around, because I think it tied it together a little bit better, at least to say, like, oh, well, you know, here's all of your basic trigonometric functions, are sine, tangent, and secant, and then you just say, now I want to do the same thing on the complementary angle, and that gets us 3 more trig functions, which, again, granted, you don't need to make 3 separate trig functions, but it makes it nice. The convention is a little bit nicer if you're not saying, like, oh, I'm going to do some sort of weird phase shifted and horizontally flipped other function here, right? I don't want to do function transformation on sine in order to get the complementary sine. Might as well be its own function. Oops. All right. So, you have anything for tonight, Super Brain? Or was that differential equation even, like, solvable? No, unfortunately. I've also been mostly just stuck with my head in correcting papers. So, goodness. Python's just getting stuck, yeah. Oops. Might as well take another look. uh, yeah, Runga Coda is really awesome in terms of being able to pretty much do anything. Um, you don't say. Yeah. When you say degree 8, does that include like all of the individual cross terms going all the way through, or is it at least somewhat reduced? Reduced. There we go. I feel like my headset dropped out. Maybe not. I don't know. Hmm. Yep, okay. Oh, I see. Yeah, I was thinking you were calling it degree 8 because it was actually something to the 8th power, but yeah, I gotcha. So, um, which page is that on? I do like this Pythagorean triple remark, though. Lemma 3.2. Proof. Ugh, I'd rather not. Look, Grant did a great video on this. Page 5. Fingerprint of the arithmetic triple described in 2.2 is this. A few different forms of the equation. Let m equal v over u, then get this stuff. Let u be r cosine theta, r v equals r sine theta. The reader's already been tricked into doing this for us before, which was the there's a clip there. Do 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 do. Oh, come on. Hey. Why, thank you. Alright, anyway. That's fun, yeah. So sine of 4 theta is equal to... No, I mean that's fine. We got yeah. Anyway. All right. Well, is there anything else you want to trick me into doing? Or otherwise, if anybody else is out there, feel free to interject if you want to talk about any other mathy type stuff. Number x is a fingerprint if and only if square root of x plus 1 and square root of, or 1 plus x and 1 minus x are both rational. That could be fun. I guess I don't, oh, right, you mentioned fingerprints in here. Right. Fingerprint of an arithmetic triple is given by this. Yeah, okay. So you're saying like that eye fingerprint. Yeah, I'm sure this is going to be incredibly not simple. That's not true. Hang on. It's not what you said. Also true, I will say. It's one of my biggest problems whenever I have some random issues that I'm working with. It's like Feels like nobody can help at all. Right, delta over c squared. Okay. But it's not this is m over n, it's that the square root of 1 plus I is going to be m over n, and square root of 1 minus I is going to be p over q, I guess. Where m, n, p, q are all integers. Right? I think that should be it. There we go. Fixed. So I mean that yeah, that's plus I is m over n squared, and then I's got to be m over n squared minus 1. So it's got to be m squared minus n squared over n squared. And plus n minus n over n squared. It's basically what you're showing. So that, sorry. So the n in the denominator here is going to have to be c from the original Pythagorean triple. That's what you're saying. I think my problem is that I'm so, oh right, because it has to be c. So it says that you've listed I as delta over S2 squared. So if that's true, that's going to be the middle number, not... So it's... Sorry. The middle number is the hypotenuse. Most people list them in order, that's why I've just... Smallest to largest. Oh, I see. Yeah, yeah. Uh-huh. Oh, but S is... Right. This is not literally in the same order because it's slightly different. Okay. Goodness. So 2ab over c squared. That's not what I want. Okay. Oops. So your 2ab really then has to be equivalent to the difference of two squares. Hmm. Technically in two different ways. Hmm. Oh, right. So that's going to be... And we already found out was c squared. Alright, let's just focus on this one then. So then m squared minus parentheses a squared plus b squared is equal to 2ab, which means that m squared has got to be equal to a squared plus 2ab plus b squared, which is a plus b squared, which was s3. Right, all of that. Okay. It's the first time that I got there, so I feel a little proud of myself. It's fine. Alright. Yeah, well. Okay. So that just means then that our stuff here has to be equal. This forces the definition of what the rational number needs to be then. Because I just said like, oh, it could be any rational number, and You said, no, no. So yeah, this is going to force, right, the square root of 1 plus I must then be equal to S3 divided by C. Or S2, I guess. S3 over S2. Right, and then over here, this is going to be similar, but maybe not exactly the same. Hang on, let's see. Right, because it can't be entirely identical, otherwise it doesn't quite work. But this might be S1, maybe? Alright, let's check. So, if we go the other way, right, this is going to be C squared minus P squared is equal to 2AB. P squared, no, hang on. Yeah, okay, I think I see it. Let's just prove it, just 100% make sure. So this is going to be A squared plus B squared minus 2AB equals P squared. So then this is going to be, right, A minus B equals P squared, which then means that absolute value A minus B is equal to P. Or absolute value of P is equal to, hang on, this is squared too, right? A minus B squared, right, okay. Technically, I guess that's how, so absolute value. Which was your S1, yeah. Okay, so then that shows us that square root of 1 minus I must be equal to S1 over S2, which you just said. Yeah. Yeah. So that, again, that forces I to be, yeah, that then forces I to be of these particular values, right? It has to be that stuff there, which we just showed. So here this would need to be, let's go back to there. This is going to be I equals M was again S3. This is S3 squared minus N was S2, yeah, S2 squared over S2 squared. Or and. You said it needs to be fingerprint, which means it needs to be and. I would need to be equal to S1. This is just going to come out to be a Pythagorean, isn't it? Oh. Yeah, sort of. What's this going to be? Hang on. That's n, so that's S2 squared minus S1 squared over S2 squared. These have to be equal to each other. S2 squared is going to drop out. You get S3 squared is equal to 2S2 squared minus S1 squared. That should also be pretty obvious, I guess, probably from just the definitions of these things. Maybe. Right, is that an obvious thing, or am I just... Okay, so S3 was parentheses A plus B squared is equal to S2. Uh-huh, okay. Twice. Oh. S2. It's just C, right. C squared minus A minus B squared. Yeah, okay. So that's, yeah. That's just from differences, or, yeah, okay. Yeah, okay. So we gotta, that's cute. All right. Gonna get a 2ab over here. We're gonna get a negative 2ab over here, so those drop. Yep. And then 2c squared is gonna be negative a squared minus b squared, which can be moved over here with the a squared and b squared from there. We just get 2 times a squared plus 2 times b squared. All right. Hang on one sec. All right, so yeah, at least like we verified that that makes sense from the from the identities, I suppose. May not help at all, but you know, whatever. It's fine. Prove anything about any characteristic equation. Huh. Oh yeah, that one. Right. so, so goodness. It's hardly fair. I haven't been up that long. I'm lying, of course. Let's see. Hmm. So that fingerprint we were just working on, is that any particular eye? Mm-hmm. So technically, like that was I sub little I, but we just didn't do any. Oh goodness. 24, 25, 25ths. Simplest. Yeah, I'm not really seeing where to go exactly from here, but yeah. So yeah, I see at the top of Appendix A we have the general one. And again, those are going to work for any. uh, yes, well, English is not exactly the perfect language for this. Does it have something to do with an identity? I mean, obviously not really, but all right. So let's see. I might. Hmm. Is there any easy way to describe the characteristic equations in terms of which ones are being selected for each individual equation? Okay, I can sort of see I1 has to do with the, well, no, never mind. I was going to say I1 has to do with the diagonals, but that's only true for like the first three. And even that's kind of spotty, it might not be true. Okay. Generically is equal to 4m sub I minus sub I cubed over parentheses 1 plus m sub I squared squared. Sine of 4 arctan of m sub I. Okay. Yeah. Maximize its presence and then try to find a uniform way to describe all of them. Yeah, since I don't have the more intimate inside out, or more intimate knowledge into all of the pieces, it makes it a little bit harder, but yeah, get it here. Why not just do something crazy for a little bit there? Yeah, well. Something's got to be ugly, right? It's otherwise it'd be super easy. It would have been figured out by now. Yeah, and I don't think this is going to work because you've got a 4 on the outside of the arctangent function, which doesn't have anything to do with like the interior part of that particular function. So right, the function transformations for arcsine and arctangent. Right, okay. Well. So 4 theta. I guess technically that would be... Right, technically that would be taking this one. Right, yeah. Okay, so then that would be taking this down here. And that would be... m sub I. I can't draw them together. Probably not. This would be m sub I, this would be 1. This would be... theta over 4. Right, but the way I drew it, it was going to end up like... making an implication as far as what this bottom part was. So I can't really do that. But if we scale it up, right? So then whatever this ends up being, it's going to be something pretty nasty. M sub I to the third parentheses squared. I mean, did you clean this up? Because then that would be 1/4 of this angle would end up coming up here, and then this distance would be m sub I times that huge square root. I mean, go for it. Okay, so where's that part coming from? So that square root simplifies to m to the fourth minus 6m squared plus 1. I'm not sure I believe you. Right, and there's only one reason I'm saying that, and that's because that's going to be... Oh, wait. No, okay. I misread that. That's what it was. Okay, yeah. I got it now. So yeah, that's an m to the 8th. And then we have m to the 6th, m squared, and m to the 4th in there. Okay. Alright. That makes more sense now. Sorry, I was looking at this, and for some, I think here, I don't think I even paid attention here. I think I was just doing like m to the 4th, and that was it. And then this was m to the 6th. So taking a square root of m to the 6th was going to get me m to the 3rd, and then, yeah, how do you get a quartic? But yeah, okay, I get it now. I will. So that's I squared minus 12 m's of I squared. 4th plus 6 and a plus 32 is going to be plus 38. So I to the 4th. And a minus 16 m to the 6th. So minus 12. Plus n sub 8. Sub I to the 8th. Okay. Well, that's inconvenient. If we did 1, 4, 6, 4, 1 going across, the 38 doesn't get divided. Did I do something wrong is the next question. 32 plus 6 is 38. Yeah, well. So, like, if this were well, no, hang on. It's not working. Right, because I'm getting 12 here, but I'm only getting 1 on either end, so... Oh, crap. Alright, cool. Plus whatever's left over. So this would be what, 1 plus m 6 squared to the 4th. Did I literally just... Yeah, I just... Never mind. Yeah, I just literally undid exactly what I had attempted to do there. This is fine. God. Alright, anyway. Just ignore that. Didn't exist. Ignore what? Don't know what you're talking about. So it's just the square of that. Right, what? Really? It's the 4th. 6x squared plus 1, all squared. Makes the 8th. Yeah, okay. Okay, cool. Yeah, because then that's going to be, this squared gets you 36. plus the other one, which, okay, yep, gotcha. See, you always believe the thing, right? Yeah. All right. So this is and we're taking the square root of all this thing. So yeah. Okay. All right. Cool. 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 So my problem is that I don't typically do this in 3 dimensions. So it's. Oy. Notationally speaking, how do you do that? Okay. Boo. So anyway, yeah. Yeah, that's probably not what I meant, but it's all cool. Anyway. So I mean, this at least implies that m needs to be small, which you probably already knew that. It's the arctangent. No, the arctangent could be anything. It's the arcsine, and it's limited, right? I know that number. Whatever. We'll deal with there being an I there. Yep. Something just blinked. Alright, so the sine of 2 theta is 2 sine theta cosine theta. So the sine of 2 parentheses 2 theta, which is just going to be the sine of 4 theta. Did we already do this? That's 4 times larger. Well, we can trade out, whatever, it's fine. Alright. 4 sine theta cosine theta times parentheses. That's cosine squared. Oh, okay, yeah. That's where you got the cube ones from, whatever. Yeah, okay. Alright. But now we have to reduce that because it's not that theta. Right, this is sine 4 theta is equal to that stuff, which means that the sine of u is equal to 4 sine of u over 4 cosine of u over 4. I regret nothing. Times 4 sine squared u over 4. it's one of the things that we do so often, is just we use u all the time, and I don't even necessarily know why. It should probably be alpha, but whatever, it's fine. No, it's in calculus, right? Like in calculus, we almost always do... Oh. Yeah. I mean, these are just sine of 1, right? So that was my problem, was I was going to be like, this is a 4. It's not a 4. That's why I should not do that. Alright, so if that is... sine of u is going to be... I mean... we could just do this. Right, that's good. Alright, so this u is going to... Ah, okay. Yeah. So this is... This is fine. So, sine of theta, this actual theta up here, it's going to be sine 4 times the sine of theta over 4. Cosine times theta over 4 times parentheses cosine squared of theta over 4 minus sine squared of theta over 4. This was an arbitrary theta. This is the actual theta. Whee! Alright, anyway. So the sine of our original theta is going to be this thing, which is our 4 times m minus m cubed over 1 plus m squared all squared. And that's going to be equal to this disgusting thing, which you already did, right? That's just going to get us the same thing, isn't it? Damn it. Right, this was m, not scribble. M over the square root 1 plus m squared times the cosine is 1 over 1 plus m squared. Yeah, we're just gonna get the same thing. Yeah, already did that. And then again, this is just literally this thing, so it's not, we're not getting anywhere, we're just going around in circles and gonna get to, like you set up above, that's just gonna be thing equals itself. But hang on, wait. Hang on, wait. Yeah, touche. No, because that's not gonna, yeah, it's not gonna matter. It's gonna do the same thing. right? Whether we're using this thing or 1, it's just going to divide out all the stuff. So yeah, because even if we try to put something else in, it's just going to fall back to the exact same thing. So, yeah, if we... Yes? Alright. I don't think there's anything else we can actually do here, right? At least not with this stuff. Because even if you try to change these to make it like, I don't know, 1 minus 2 sine squared of theta over 4, like that's still not going to do anything. Yeah. Alrighty. Well, at any rate, might be done for the night. So let's see who is out there and available for tonight. I know Jason Charles Miller is on for at least a little while. Looks like he's here at least for a little bit longer. Nah, don't worry about it. I'm doing alright. It's just, yeah, starting to get a little bit late. Then when you run into exactly the same thing you started with, it's kind of like, come on now. Alrighty. So, thank you, Superbrain. Have a good week. Well, I guess have a good couple of days. I'll probably either see you on Friday or see you on demand. So get some sleep, have some fun. Good luck, and thank you to everybody else who's out there. Anybody who stopped in, anybody who's on the video on demand. Thanks, you're really helping out and all that good stuff. So I'll be here on Friday for. Let's see, I think I said I was gonna be doing some other games. So we'll see how that goes. I'll figure out what I want to do. Figure out what I want to do with my life. It's a whole nother question. But at any rate, so I'll see you later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night, and I'll see you around.